Guys, in this session you will get to know how to build your own language and a compiler for it. To build your own language, you need to understand attribute grammar. Attribute grammar is developed by Donald Knuth. Attribute grammar is responsible for construction of compilers and interpreters. It is used at various other places. So before proceeding further, I would like to quickly introduce about what is attribute grammar. So attribute grammar, as I've already told you, is introduced by Donald E. Knuth and since then have proved to be very useful in specifying the semantics of programming languages, in automatic constructing of compilers and interpreters, and in specifying and generating interactive programming environments, and in many other areas. Attribute grammars are a generalization of context-free grammars, in which each symbol has an associated set of attributes that carry semantic information, and with each production a set of semantic rules with attribute computation is associated. An attribute grammar consists of three things: a context-free grammar, which is represented using G, and a context-free grammar has four important things: T, N, S, P, where T stands for terminal symbols. Terminal symbols are symbols which can be variable names, which can be procedure names, which can be constant names. These are also known as identifiers, and these terminals can be operators. These terminal numbers can be integers or anything. Followed by the second thing in a grammar which we have is a non-terminal symbol. A non-terminal symbol is a variable which will always be there on the left hand side of your programming statement or the statement of your high-level source code. Followed by we have S, which is the start symbol and which doesn't appear on the right hand side of any production rule, and P is a set of productions. So P can be considered as a set of tokens which has been generated after reading each character and each keyword from a high-level source code by your lexical analyzer. So this is a context-free grammar which has to be defined within a phase known as lexicon, followed by a set of attributes AX for each non-terminal symbol X from set N. N stands for non-terminal symbols and A of X is a attribute. So attributes are of two types: inherited attributes and synthesized attributes, and you are going to understand them. Followed by you need to have a set of semantic rules known as R. So you can have as many number of semantic rules in your code. Semantic rules are defined within the scope of a single production. A production is again a set of tokens or a statement. A finite set of semantic rules RP is associated with the production P, with exactly one rule for each synthesized attribute occurrence and exactly one rule for each inherited attribute occurrence. Therefore, an attribute grammar is a triple, which means attribute grammar is equal to GAR, where G stands for context-free grammar, A stands for attribute, and R stands for semantic rules. So now, let me just quickly take you here. So now as you understand about attribute grammar, so I can quickly write here, attribute grammar could be considered as G, and it is a set of three things. Attribute grammar can be considered as AG, and it is a set of G, A, and R. So G stands for context-free grammar, A stands for attributes, and R stands for semantic rules. So now here what you will have in the lexical analysis phase, this phase is going to be the G phase. We call it as context-free grammar. Context-free grammar. So let's say let me just quickly write the initials. In syntax analysis phase, syntax analysis and semantic analysis are done at the same place. So it considers attributes as well as the rules, and here there are certain things like rule semantic functions are defined within the rule. So these are the three levels which you have to understand. So using attribute grammar, you can quickly create a language or a compiler for that language. Now you have to understand what is lexical analysis, what is syntax analysis, and what is semantic analysis. As I've already told you, lexical analysis is responsible to read the high-level source code keyword by keyword and generate a token for it. This token is a number, and once this number has been generated, then it is sent to the syntax analysis phase. So you have to understand how we are going to read the source code from the high-level language keyword by keyword, and how it is going to be converted into tokens or numbers. So this will be done in lexical analysis phase. So let me just quickly introduce you how lexical analysis looks like. So here is a program which you will be writing and I'll be explaining you quickly, but before that I will show you lexical analysis. So lexical part of new language is defined with the reserved word lexicon. Okay, so you can see that it has to be defined with lexicon. So within a language, you're going to use a keyword known as lexicon, and within this your lexical analysis or part will be defined. Now, so from the part, you can use any of the programming language like Lisa, like Java, in order to build up your interpreter or compiler. So I'm using Java source codes here. So a scanner or a lexical analyzer will be created in Java source code in this demonstration. So tokens are defined with the named regular expressions. So as you have already heard about regular expressions, using regular expression you can perform pattern matching. So within the lexicon phase, what we are going to do, we are going to define some regular expressions, and these regular expressions will be responsible to read the source code and convert it into tokens. Now, so in lexical analysis or scanning, the stream of characters representing the source program is read from left to right and grouped into tokens. The lexemes matched by the pattern for the token represent strings of characters in the source program that can be treated together as a lexical unit. Regular expressions, which are the most frequently used formal method for specifying patterns, are also used either in Lisa programming language or in Java programming language. So we are using regular expressions in our own code for Java programming language, and regular expressions can be uniquely represented like this, wherein you can define name for the regular expression as well as you can define the regular expression. So you're going to understand that part as soon as we progress further, and it has to be defined within the lexicon phase. So now let's quickly take you back. So here is a representation of an attribute grammar using which a language can be generated. So now if I show you, within attribute grammar you can use a keyword known as language, and you can define name of the language in order to build up your own language. Now once you are creating an attribute grammar, it has three phases. The first phase is context free grammar, the second phase is attributes, a finite set of attributes, and the third phase is a finite set of rules. Apart from that, there are other few things like point cut and advice, which you can ignore at the moment, and you can understand them as soon as we progress further in our course. Now, so attribute grammar is a triple which includes context free grammar, attributes, and a finite set of rules. So now we are going to get started with writing our own language, and we are going to implement lexical analysis on it. To do that, I'm going to open Notepad editor. Within Notepad editor, you can quickly get started with writing your own program. So I'm going to write my own language, and let's say build Hackveda language I'll be using attribute grammar, built by Donald E. Knuth. So Donald E. Knuth has developed attribute grammar, and we are going to build our programming language using attribute grammar. So as far as attribute grammar is concerned, there is a keyword known as language in attribute grammar to create your own language, and you have to define name of the language. So I'm going to define a language with the name Hackveda. So Hackveda is the name of my company, and I would like to create a language for my own company. Now, once we're done with this, so your attribute grammar consists of three phases. The first is context free grammar, and this context free grammar is known as G. Okay, you can call it as G. Second, it contains attributes. Let's call it as attributes. And third, it contains, let me just quickly type that here. Third, it contains finite set of rules, and these rules are semantic rules. So these are the three things which are available in an attribute grammar. So let's get started with the first one, which is known as context free grammar. So context free grammar can quickly be created in attribute grammar for building languages using the keyword lexicon. This part is also known as lexical analysis, context free grammar, or you can also call it as lexical analysis. So as far as lexical analysis are concerned, you have to define your regular expressions here. And these regular expressions will be responsible to read the high-level source code. So as far as Hackveda language is concerned, at the moment what I want is, I want to make a simple mathematical language wherein I am going to perform some operations like addition, subtraction, and my Hackveda language is going to do that. So to do this, what we are going to do, let's say we are going to create a number. So this number, we are going to read numbers from the source codes because it's a mathematical language. So I have written name identifier for my regular expression as number, and now we have to read the numbers. So we have to read the source code and we have to read the numbers from 0 to 9. Okay. So using this regular expression, we are going to read the numbers from 0 to 9. Once we have read the number, now what next we need to do? We need to read the operators as well, because since it's a mathematical programming language, then you will be having various operators like plus, minus, into, divide. And plus, minus, into, divide has special meaning in languages, so we need to use an escape character also. To do this, what we are going to do, we are going to define operators. You can use any names for defining your regular expressions. So I'm defining operators here. So we have to escape these operators as well. So first of all, I'm going to use this escape character and I'm going to use the plus operator, because I would like to treat this plus as a string here, and it has to be matched exactly if it exists in the high level source code text. So now we are going to identify the plus operator. Moreover, we are going to identify, let's say, minus operator. Moreover, you are going to identify the into operator, as well as you can do search for mod operations, for division operations, and various other things. Okay. So here is an escape character just to identify the plus operator, followed by a pipe operator, which means an operator could be plus, it could be minus, or it could be into individually. Okay. So this is the second operator, or it could be a third operator. So we have identified operators using regular expressions. Now, once the operators have been identified, now what we need to do is, in a programming language, as you all have seen, that some people type the code with white spaces and other people type the code without white spaces. So now what we need to do is, we need to identify white spaces in the code as well, and then we have to ignore it so that there is no syntax errors. Now to do this, what we are going to do, we are going to identify white spaces using regular expressions. So let's say we are going to define the named regular expression, and this name of this regular expression will be white spaces. And to create a white space from the content, we are going to read the content. We are going to use the escape character, and we are going to find out the single space character. So this is a single space character which we are going to search for. Followed by, we are going to search for line feed. So the line feed can be quickly accessed using an escape character followed by OX OA. So you can have a new line, then you can have a line feed OX OD, and you can have the horizontal tab 0x09. So we have specified various characters like a single space, a new line character, followed by the line feed, followed by hexadecimal representation of horizontal tab. So in case if there is any white space in the program, we have to ignore it. To ignore that, you have to quickly type in the keyword ignore, and you can quickly define white spaces. So now white spaces will be ignored within this. In general programming languages, you have seen that people remove comments from the language. So you can also define one more regular expression to find out comments, and you can ignore comments also. Now, so once this is done, your lexical analysis part is done. This phase is known as lexical analysis, where we read the source code written in high level language using regular expressions, and we convert them into lexemes, and these lexemes are known as tokens, and these tokens are also known as numbers. So these numbers, when they are grouped together, they are known as production. Okay, so we'll see that as soon as we progress further in the course. Now, So here you can see that we have defined a new language known as Hackveda, and we have defined the lexicon part, which is our lexical analysis part, wherein we have implemented regular expressions, and using regular expressions we are going to read the high level source code, and we are going to convert these high level source codes into lexemes, and these lexemes are also known as tokens. Token is a number for each keyword written in your high level source code. Now I would like to take you back to the next step. So you have written the context free grammar. Now we have to go to the syntax analysis phase. Okay, let's understand what is syntax analysis. So here is syntax analysis. In syntax analysis, tokens of a source program, which means your numbered tokens or your lexemes, are grouped into grammatical phrases. Okay, so you have seen that a parse tree will be generated, and the grammatical phrases will be formed. The task of syntax analyzer or parser is to determine if a string of tokens can be generated by a grammar phrase. The syntax of the programming language is usually described by the well-known BNF notation. So you're going to use Backus NOR form in order to create the syntax for your programming language. Okay, so we create the syntax for our programming language using Backus NOR form. So in Lisa programming language, standard BNF conventions are followed, but what we are doing is we will be using Java programming language. So within Java as well, standard BNF conventions are followed. So here is the standard BNF convention, which you can see. On the left hand side, you have a non-terminal symbol, followed by you have this assignment, followed by you have a set of production, a set of lexemes or a set of tokens. Okay, so what we call it as, you call it as a production rule, and you can have various production units here in one specific expression. Okay, so this is what syntax analysis is. So whatever syntax you define, that syntax has to be followed by the source code. So you can define the syntax rules within your programming language when you are creating your programming language using attribute grammar. So let's see how we are going to do that. Okay, so now we are going to define the syntax analysis, the syntax rules in our language. So here what we are going to do, we are going to define syntax for our language, and this phase is known as syntax analysis phase. Okay, so syntax analysis phase is done by creating an expression. These expressions should be created within the semantic rules. In order to create a rule, we use a keyword known as rule. Okay, so let's do that. So let's quickly do that. We're going to define a rule. Let's call it as rule 1. So we are going to define the syntax rule here. We also call it as syntax and semantics. So we are creating a syntax rule, and we are using BNF. We call it as back norm form, Backus NOR form for syntax of the programming language. Okay, you can quickly check that on Wikipedia. So using BNF, we are going to set the conventions, the syntax conventions for our programming language. Okay, so in rule 1, the first expression which we are going to define is, since it's a mathematical equation, what I want is, I would like to create a rule wherein I will be having an expression, let's say E. This expression will be generated using an expression known as E plus E. So this is going to be my first Backus NOR form expression. So this is the syntax of my language. So if somebody types in an expression plus another expression, then the syntax is correct. So this is going to be my first rule. This is going to be my first rule. So let's just quickly define as, this is going to be my first rule. In the same way, I'm going to define various other rules. Let's say I'm going to define another rule, let's say E minus E. Now this is going to be my second rule. So these are my syntax rules. If somebody types in E plus E, it's a right syntax. If somebody types in E minus E, it's a correct syntax. But if somebody writes E into E, it is not going to be the correct syntax at the moment as far as my Hackveda language is concerned. So I have defined two things, followed by I'm going to have another syntax. Let's say if somebody types in a number, so I'm going to save that number here. Okay. So this is going to be my third rule. If somebody, since it's a mathematical operation, as in Python, if you have seen, if somebody types in an integer value and presses an enter, so that integer value is stored into the variable or the register and it is returned back in form of a print statement. So we are going to have that feature in our programming language wherein we have defined a number and we are going to store it into E. So this is like the syntax analysis, and we are following the Backus NOR form for defining the expressions. Okay. So now, since we have defined the expressions here, we are going to have a few more rules. Since syntax analysis, the semantic analysis has finite set of rules, you can define as many rules as you want. So let's say I have defined another rule. So this is going to be my rule 2, and within this rule I'm going to have some more information. Let's say, so within this rule, what am I going to do? I'm going to have a keyword known as start, and this keyword start will contain the value of E. So this is going to be my another rule which we are going to utilize. So in case whatever value whatever value we have got from a number or from an expression, that is going to be stored into E, and that E value we are going to store it into start. So start is going to be a non-terminal and it will be printed. So start is going to be a start of your program. Okay, you have heard about start symbol, so this is that. Now, so once we have got this information set, now we need to proceed to the next phase. So we have defined the rules, the set of rules we have defined, and we have to define the attributes also. Okay, so now let me just quickly show you how attributes will be defined. Now, since you can see that here we have the expressions E which are going to be added, so they have to be an integer type so that they gets added and they are stored into this expression E. So this expression E should also be of the type integer, and in the same way the start should also be of type integer. So now what we are going to do, we are going to define some attributes in syntax analysis before the rule phase. So how we can do that? We can quickly define attributes, and you can quickly define the type of the attribute by specifying integer. Okay. Now if you would like to see the language representation for that, you can quickly see that attributes can be defined using the keyword attributes by defining type of the attribute which you are defining, followed by the finite set of attributes. Okay. So what we are going to do, I'm going to define that. I have defined attributes, I have defined the type as integer, followed by I'm going to have start.val. This is going to be an integer value. Whatever values of start we have, it is going to be an integer. Whatever values of expression E we have, that is also going to be an integer type. And you can see that attributes does not need a syntax at the end. So what we can do is we can remove it from here. Now, so here in syntax analysis, as I have already told you, A and R will be defined. So attributes we have already defined and rules we have defined. Now we need to go to the next segment, and which is the syntax analysis you have already done, and you can see that as far as the BNF notation for syntax convention is concerned, here are various other syntaxes which can be defined. So what I have done is I have defined a syntax for my language which is going to be the standard convention like expression plus expression, expression minus expression, and various other. Now followed by this, now we need to go to the next step, and the last and final step is the semantic analysis, wherein we have to define the functions, the semantic functions, using which we will understand that the expression which has been specified in the source code, what is the meaning of that expression and how a computer should understand that expression. So for this we write semantic functions and we compute semantic functions whenever an expression is encountered by our syntax or semantic analyzer. To do that, what we are going to do, let's go here to our code, and now we are going to perform our semantic analysis. Okay, so here we are going to perform semantic analysis. So what exactly semantic analysis is? You have to write semantic functions. To write semantic functions, and these semantic functions will be responsible in order to make sure what a computer has to do. So in order to write an expression, so these semantic functions are associated with each semantic expression which you have defined here, and you can quickly define that using compute keyword, and I'll show you the language, the convention for that. So here you can see that whenever we write a rule, you have to define name of the rule, and within that name of the rule you can have your expression, which is our syntax convention made using Backus NOR form, followed by you have to define a compute keyword, and using this curly braces you can define a semantic function. There can be n number of semantic functions defined within your code, followed by an execution operator at the end. To do that, let's go here. So we have defined a compute function and we're going to define it. So now for the expression e plus e, how it has to be treated, this has to be defined here. So this is a mathematical, this is the semantic function which has to be defined, and you can code it. So using Java language, I'm going to define my assignment statements and my execution statements. Okay, so you can use any of the languages like C, C++, Fortran, Pascal in order to build up your new compiler, and I'm using Java programming language to build up my new compiler. To do that, what am I going to do? So I'm going to use e.val. So let's say we have two expressions here, e plus e. So what am I going to do? I'm going to take in e1 dot value. I'm going to plus e of 2 dot value. So both the expressions have been taken, and I'm going to store them into e dot value. So I'm going to take the values of these expressions and I'm going to add it, and I'm going to store it into e dot val. So this is going to be my Java method, and this is going to define my semantic function. So now whenever somebody in a high level source code has written any expression plus any expression, which means let's say 1 plus 2. So 1 will be treated as E1, 2 will be treated as E2. Let's say I'll take some other example. Let's say if I have to add 10 plus 20. So I will define it in the sequence somewhat like this, 10 plus 20. So syntax analyzer will identify whether my syntax is correct, and post that if the syntax is correct, then the values of E1, which will be 10, the value will be taken. It's of integer type. We have already defined that in the attributes. Followed by the second expression E2, and the value will be taken. The value was 20. So 10 plus 20 will be done, and it will be 30, and we are going to store that into a value of 30. Now since this value is stored into 30, now we have to quickly display this value as well. Okay, so we are going to save this e dot value into the start value. So in the rule 2 we have defined that if there is something in e, we are going to put it as the start symbol, and we are going to define the value. So let's write the semantic function for it. So within this we are going to define the semantic function, and let's do that. Let's remove this. So within this we are going to define the semantic function, and the semantic function says you're going to get the value of start, and you're going to put e dot value into it. Okay, so we have defined the statement in Java programming language, and now my computer or my machine will understand that in case if there is an expression identified, you put that onto the start convention, start non-terminal, and it will be executed. Okay, so we have defined these values. Now what next we are going to do? We have two more expressions here, e minus e. We have to define a rule semantic function for that as well. So within our semantic rule we are defining the semantic functions, as you can see. So since it's a minus, so we are going to define e dot val is equal to e1 dot val minus e2 dot val. So we are going to perform subtraction here. followed by, here we do have a number. So what we are going to do, as soon as a number is passed from the high level source code, we are going to read its value, whatever the number is. Then we are going to store it into, we are going to convert it into an integer, and we are going to store it into an expression, because expression is of integer type. So what we are going to do, we are going to read e.value, and we can use hash number. So we can select hash number, we can get its value using this function, and then we can convert this value into an integer. So to convert this value into an integer, we can quickly call the Java class integer, and it has a function known as value of. You can define that function, and as an argument you can define the number value. So let's say whatever the value of the number is, it's a string value, it will be converted into an integer, and once it is converted into an integer, it will be stored into e.val. And now finally this e.val will be stored into our start value, and the value will be printed as soon as we are going to execute our programming language. So now, as you can see here, all the things have been done. So now, as far as attribute grammar is concerned, using attribute grammar, we have performed lexical analysis, wherein we know what kind of data we are going to read from source code. Any data apart from these three things like numbers, operators and white spaces will be treated as an error, and the error handler is going to handle it. Once the tokens have been read, from here a symbol table will be generated, and within that symbol table you will be having your identifiers, variables and your constants. Now, so these, you will be having attributes and a set of rules, and using the set of rules the expressions will be matched. If the expressions matches appropriately using the lexicon which has been specified at the top, then it means your program is syntactically correct. In case if your program is syntactically correct, then the expression will be evaluated, and this evaluation will be done using semantic function, and this will be done by your machine. So machine is going to understand that if the expression is e plus e, then it means it has to be added, and once it is added, then we are going to generate the output for that. Okay, so this is how you can quickly generate a compiler or a language of your own. So now, since I have made this language here, now what am I going to do? I'm going to make a compiler using the set of code which I have written here. Okay, so what am I going to do? I'm going to copy this, and I'm going to generate a compiler using my build tool. So to do that, what am I going to do? I'm going to go to my build tool which I have available here. Moreover, so I have my build tool available over here, and I'm going to paste my code here. Okay, so I have pasted my code here into my notepad editor here, wherein I'm going to build my language. So just a quick check of what we have done. We have used a language keyword from attribute grammar. We have defined name of the language, followed by we have defined the context free grammar using the lexicon keyword, wherein we are going to read the numbers, we are going to read the operators, plus, minus, into. We have not used into at the moment because we have not defined any expressions at the bottom, but still we are reading the operator. So reading into can be done, but nothing will be executed on it because we don't have an expression or a rule for it. Then we are reading the white spaces, and we will be ignoring the white spaces from our program. So anybody is free to write their codes with a proper representation using white spaces, tabs or any other thing. Followed by, we have defined the attributes of our expression variables, whatever identifiers we have. So the attributes have been defined, and post the attributes we have defined the semantic rules as well. Using these semantic rules, we have defined the expressions using Backus-Naur form, and syntax analysis will be done using this Backus-Naur form. Once syntax analysis is done, then semantic analysis will be done using these expressions, and the evaluations will be done, and machine will be able to execute an addition operation if it encounters an expression somewhat like e plus e, and it is going to perform a subtraction if it receives an expression somewhat like e minus e. So we are going to do that. So once we have this, now we are going to build our language. So this language will be built using our attribute grammar build tool, And to get this attribute grammar build tool, you can quickly reach out to our website hackveda.in, and you can talk to the mentor. And if you are a subscribed user with us, if you are a paid subscribed user with us, you can get the build tool from us. Now, so we are going to build this. Now the build process has been started, and let me just quickly show you how the build process looks like. So here it says that the lexicon is expected. So I'm going to do one thing. Let me just quickly do that. You need to put a space here, because lexicon and white space is considered. So lexicon and this will be treated as one single thing. So you have to put a space here. Okay. Let's build it again. So we are building the program again. And let's go to the bottom, and let's say lexicon expected. At the bottom, compilation status has some error. I guess I missed something while copying. Let me just quickly check that. So I do have, let's just quickly check the brackets. So you have one bracket here, then you have defined the lexicon ends up here. Then you have defined the attributes, which is there. Then you have defined the rule, which we started here. And we have e plus e, which we computed here. E minus e, we computed there. We have a number, we computed there, but we don't have a end of the rule here. Okay. So let's just define the bracket here to end your rule 1. Followed by, you'll have rule 2, so which will end up here, rule 2. Followed by our language bar. So we're going to save it. Once the save has been done, now we are going to build that again. So let's build it. So now we are building the tool again, and let's quickly check. So we have e dot value, we have defined it appropriately. We again have a rule here. Okay, rule 1. So at the end of the rule, we'll quickly check if we have the rules written appropriately. We have the first compute rule, the second compute rule, we have the third compute rule, which we have not defined here. Let's do that. Compute and start a bracket. So the bracket ends up here, and followed by your integer rule 1 ends up here. Then you have second rule here. Okay. Followed by your, if the rules have been end, let's put that here. Let's remove that. Save it, and let's build the code again. So okay, that has been changed. Now what we're getting is lexicon has been expected and end code is expected at the end. So rules have to be defined with an end statement, and you need to have a bracket here. So that's one thing which we need to add. Then we have the second compute rule, we have the third compute rule, we have this Java compute code, and here is the rule 1. Let's just quickly save that again. File, save. Let's build it. Lexicon expected. So somehow the lexicon is expected here. So we have it somewhat like this. So let me just remove one of these. Let's just remove the comments out of here. So you have the lexicon here, and after the lexicon we have the numbers, operators, white spaces, and this. Yes. So now let's save it and build it again. Somehow I guess we have We are missing one variable. We are missing one curly brace here, I guess. So let me just quickly check the curly braces again. So here I have done the compute statement, e compute, e.value, I have closed it here. Then I have the second statement, I have closed it here. Then I have done the third statement and I have closed it here. And I have this rule 1 and rule 2. So I have the rules here. Let's just put the rules here. e.value, e1.value, we are following the appropriate Backus NOR form. So we have the language, we have the lexicon. Okay, let me just quickly check that again. Let's just build it again. So we have that error line number 5. We are expecting this 2, 3, 4, 5. Suppose that what we can do is we can put in an attribute as execution operator at the end, and let's just try saving it, building it again. So here, due to attributes, it happened. So now what you need to do is you need to make sure that you are defining the attributes properly. So now here at the bottom you can see that the compilation process has been done, and let me just quickly show you how it has been done. So what exactly we have done: generation added, cannot parse this grammar. We are getting one issue that we cannot parse this grammar because when it was trying to shift reduce, then the plus operator was being identified with the parser. So we need to change the parser. Okay, to change the parser, let me just quickly go to the options and the compiler options, and let me just change the options. We are going to parse the abstract syntax as well. So now we are going to build it. Okay, so let's build it. So now once we are building it, now you can see that the symbols have been parsed, the compilation has been done, and now you can see that compile.java program has been created within a directory known as out java compile.java, and you can see that the compiler has been generated now. So if I quickly show you that the compiler for my language Hackveda is now ready. So using attribute grammar, I have used the keyword language. I have defined the name of my language. Name of my language was Hackveda. You can quickly define it somewhat like Python, C++. You can make any of the languages again. Now, so as far as I started my language, then I need to define the lexical analysis part. So I have defined it using lexicon, wherein I have defined my named regular expressions. And using this named regular expressions, we were able to read the source code which has been written. So once the source code has been read, it has been converted into tokens. Now these tokens are converted into production. So this is done using syntax analysis tools and semantic analysis tools. Once that is done, once it is given to syntax analysis tool, then in the syntax analysis, we have identified whether it follows the language syntax convention. So the language syntax convention is made using Backus NOR form, and here is the expression of BNF convention looks like. So we have defined it. So once it is defined, then we have performed semantic analysis, wherein we have quickly checked that how exactly the value will be computed by the machine. So once we are done with that, now what we can do is we can utilize this language, and we can utilize this compiler to compile a language which is written in Hackveda language, which can understand this. So now in order to do that, what we are going to do is, once my compiler is ready, I'm going to quickly show you how my compiler looks like. Okay, so my compiler, since I was using Java platform and I was developing my compiler using Java programming language, so we have got a compiler ready, and now using Hackveda language, anybody can write a program and it can be compiled, and the object code will be generated. Once the object code is generated, then it can be sent to a linker so that an executable file can be prepared and anybody can use it like a software. So now, in order to do that, I'm going to quickly define how this compilation process will be done. So if you have ever compiled a Java program, so you will be able to understand that using Java compiler, you can compile your programs. So now what am I going to do is, I'm going to make use of my Hackveda compiler class. So this is created within my directory compiler design, within the directory out, within the directory Java. If I search here, you can see that I've got a class known as compile.java. This compile.java is my compiler which I have just generated, and this is the compiler for my Hackveda programming language. So using this compiler, now I can compile any source code written in Hackveda language. Okay. So what a Hackveda language is? Hackveda language is any mathematical equation which contains plus minus operator or numbers or white spaces that can be processed using this compiler. Okay. So now what I can do is, let's say I'll go to my main directory compiler design and I'm going to write a new program. Let's say this is going to be a Hackveda program written by a programmer, let's say. Okay. So let's say somebody wants to use my Hackveda language and he wants to write a source code in a high level language. So let's say he can quickly open Notepad editor. So within this Notepad editor, we are going to write the code in a high level language. So let's say I say something like 30 plus 40. So I've written an expression. Okay. So now how this 30 plus 40 will be treated? So this is going to be the source code 30 plus 40, which I have written over here. Now this source code is going to be compiled into a machine code. Okay. So this was the high level language code. 30 plus 40 is the high level language code which I have just written. Now using my compiler, I'm going to convert it into a machine code. So how it is going to be done? So I'm going to compile it using my Hackveda compiler, and to do that, I'm going to use Java. I'm going to use the class path. So using the class path, I'll select out class. Within this out class, I have a directory known as classes, and from this directory, all the files which are available in this directory, like the parser, the compiler, everything is available in form of .class extension which we can utilize, followed by the generator.jar file using which we're going to compile using which we're going to run our program. So it will be done, followed by I'm going to define name of the compiler. So name of the class will be the compile class which I'm going to execute over my program Hackveda program.txt. So over Hackveda program.txt, now we are going to compile our Hackveda program written in Hackveda language using the compiler which I have just generated using my language attribute grammar. Okay. So now we are going to do that, and now let's run this program. So now once we run this program, let's go here, let's run that. So now once we run that program, you can see that Hackveda.start has been executed, and once this has been executed, we have got the value as 70. Okay. So now you can see that we have written 30 plus 40 and we have got that executed. Okay. Now if I say I remove this white space and I write 30 plus 30 and I save it, and if I compile and run the code again, so this time you can see that the result is 60, which means white spaces have been ignored. Okay. Now if I write something like minus 30 minus 20, let's say, if I save it again, and if I again compile my program, you can see that I've got the answer like 10. So both the expressions are being evaluated. So now let's say if I type in into, so into will be taken, but I'm not going to get a result because we don't have an expression multiply for it. Okay. So let's just save it and let's just clear it. Let's just run it. So now once we run that, you can see that the parsing has been done. There was no syntax error in parsing, but semantics cannot produce a result. And this is because the semantic analyzer identified that there is no such expression available. So syntax and semantics issue has been encountered and no output has been generated this time. Okay. Now let's say if I do something like divide, so this is nowhere defined in my code, okay? So if we do that, if we try to build that, what we get, again, there is no output, there is an error, okay? So that has been, this you can access using the error stream. So this is how you can quickly see that this thing can be done, okay? So I have written a programmer. Let's say if I use a tab space, I press plus. If I use another tab space, if I use Control S, and if I run the program again, if I compile the program again, you can see that I get 50 as my output, okay? Now, so earlier we were not getting the multiplication. So what I can do is I can add a multiplication feature to my language. So now what I can do is I can go to my rules. I can quickly see that I have the rules available over here. For this, let's say I would like to create a new rule. E will be, let's write a new rule, E into E, and we are going to perform the semantics for it. So we are going to write a semantic rule here. So E dot value is equal to E1 dot value. We are going to multiply that with E2 dot value, okay? So now this is being done. What we are going to do, we're going to save it and we're going to build our language again, okay? So now once we are building our language again, now you can see that the compiler, a new compiler will be generated for my language, and once the new compiler has been generated here, now this time if I write my code for into, if I replace 30 with into, and if I save it and if I compile the program again, so now this time you can see that I get the response 600. So this is how you can quickly create your own programming language using the attribute grammar. So now you can see that you can use attribute grammar to build your own compiler. You can design a compiler. A compiler is a program which converts high-level language into a machine code, and to do this it has three functions. The first function is lexical analysis, the second function is syntax and semantic analytics, and the third function is code generation and optimization. So the first step, lexical analysis, you have two parts. The first part is generation of tokens and second part is generation of symbol table. So once you do your first part, generation of tokens, what exactly you can do, you can quickly perform the steps and you can quickly analyze that. So I can quickly show you the stuff as well, that how it has been done, how the tokens are generated, how symbol tables are created. You can quickly understand them as soon as we progress further. Now, so once it is done that you have performed lexical analysis for generation of the tokens and for generation of the symbol table, then it can go to the next phase, which is syntax analysis phase. In syntax analysis, we try to match the convention of the language using Backus-Naur form, and whatever syntax you have provided, it is going to match with under the lexical analysis phase. And you have defined the semantic rules where you have the production, which we also call it as the expression, and we have also defined the semantic functions, which actually performs that what is the meaning of that expression and how the computer has to execute it. Okay, so this is how you can build your own language. In this demonstration session, we have developed Hackveda language, and we have used Hackveda language in order to perform some basic mathematical operations of plus, minus, into, and we have done the compilation process, and using that compiled code we have got our objective results done. So this is how you can quickly build up a compiler using compiler design techniques. Thank you so much for watching.